Good evening, everyone. This is Celso Batalha, Evergreen Valley College, and this is ASO 10, the online lecture. And we are basically wrapping up the semester. And in fact, this week we are diving into the subject of stellar evolution. And before we go there, I would like to thank you, lots of you who did the survey on the use of our textbook. I'm using these textbooks, OpenStax, not only in astronomy, but also in physics, and the results have been encouraging. Um, what's the main argument, the main point in stellar evolution, and especially if if you recall the discussion that is ending tonight, mass is the important drive in stellar evolution. Stars that are more massive, they go through their evolutionary stage much quicker than stars that are low mass. Low mass stars, they take very long time in their contraction phase towards the main sequence. And when they reach the main sequence, and that is where stars spend most of their lifetime, 80 to 90%. So when they reach the main sequence and when fusion reactions start taking place in their very core, um, a low mass star like the sun stay 10 billion years, but a high mass star can go much faster, a few 100,000 years, few million years, depending on their initial mass. And what also differentiates the evolution of the stars, not only the time it takes them to complete their cycle, but also the uh, the end, the type of death they will go through. So low mass stars have a somewhat mild death with some bumps in the road, as we will see, and high mass stars they have some explosive death we call supernova. Regardless if low mass star or high mass star, by now you should know the importance of stars in the universe in general is not only to stand as the luminaries of our sky, but also those responsible for producing atoms. So if you look around ourselves, I look around my room, a place that I am now, probably you are in your house or your cell phone looking at it. Um, all this environment, with the exception of hydrogen, helium is not abundant in our environment, I don't think. But with the exception of hydrogen, you can find in abundance in water, in vapor. Atoms in general came from stellar processes, so from processes that exist primarily in stars and more particularly associated with their energy production. So in this opening picture, you have a nursery of star formation. All this gas, right and left, indicates places where stars are going to be formed. So basically, this subject should be pretty much enrooted in your understanding. Stars came from cold gas, dust, and the action of gravity. If gravity can overcome gas pressure, then contraction takes place. But in addition to gravity, rotation also is an important ingredient that leads to the formation of a circumstellar disk around the star, and out of this circumstellar disk, smaller bodies like planets, satellites, and asteroids and comets come to be formed. And eventually we have a star system. So you can see the gas and dust that will form stars, but you also see a cluster of newly formed stars. So what is interesting when you look in the central part of this picture, the cluster is already um, pretty much devoid of its parental cloud, if you will. The cloud has been consumed in stars and can and has been also expelled and swept out by the stellar wind and by the stellar radiation itself. So in this chapter or this week, we are pretty much focusing on the end of life of stars. And I have a video here that is interesting that um, show the dance of two stars. So you have a binary system, and then basically the end of life here is to explain how supernova type 1 is formed. So what is the evolutionary stage of a low mass star? So a low mass star, and most of you complete the discussion, and by now I know you can repeat all the basic steps. So you have the cloud out there, you have gravity bring star gas to the central and formation of star. Eventually the star core is hot and dense enough to ignite fusion reactions. So eventually the hydrogen in the core is depleted because hydrogen becomes helium, and energy is used to sustain the star for most of its lifetime. But eventually, the hydrogen in the core is exhausted. Now you have a helium core, and then the star undergo transformation. So basically, a helium cannot be fused at a low temperature, which requires the core to initiate its contraction because of the weight of the star above. So the core contracts, heats up, so temperature goes up, and then initiates a fusion of hydrogen in the shell surrounding the core, and the core is inert. And that excess of energy forces the outer layer into some expansion. And then we call that phase red giant phase. Though the outer gas expands because reduce the interaction and collision among molecules and atoms existing in the atmosphere, the temperature goes down. And by now you should remember that lower temperature means a redder type of emitting gas. And then the star becomes red. We call that red giant. And in a following phase, eventually the core flashes and fusion reactions of helium carbon initiates because now the temperature is high enough to allow for this type of fusion reaction. Now, once the helium in the core is totally depleted into carbon, again, this process repeats itself. The core contracts but cannot heat up anymore to fuse carbon or oxygen into heavier atoms, and the core becomes what we call a white dwarf. Once the outer layers are expanded and expelled, and we call that a planetary nebula. So that is the normal steps in the evolutionary stages of a low mass star. And you are going to see in this video exactly this happen. The primary star, which is evolving faster, both of them are low mass star. Again, the primary star that is evolving faster becomes a planetary nebula. And then you're going to see its core revealed as a white dwarf. And then it zoom out, and then you can see the nebula, the planetary nebula surrounding this binary system. And then you zoom in again, and then the secondary start transferring mass. And then the primary cannot be more massive than 1.4 solar masses, which is the Chandrasekhar limit. And then the star explodes, and we call that supernova type 1. So let's see that happening. And they are dancing happily, And now this fellow starts to evolve and eventually losing its mass. Keeping losing mass. And the gas is expelled, and then now you have the white dwarf right there. Now this fellow here got some extra mass. It became a little bit more massive, and now you have the planetary nebula kind of a zoom out. It's cool, huh? Very cool. And then you go zoom in again, hopefully. There you go. Now this is the white dwarf, and now this fellow star, which became a little bit more massive, now is evolving too. And eventually it's going to start losing its fuel in the core. So hydrogen is going to be exhausted, and then this process of contracting core and expanding outer shell will occur, and eventually the mass will start transferring. Now you can see down here the limit, the Chandrasekhar limit. And then you have the bipolar flow coming in. This is very high density region, and kaboom, you have a supernova type 1. Supernova type 1, when we study later um, uh, the expansion of the universe, we will see it as an important component. Let me stop this. An important component to establish distances and scales in our universe. As opposed to supernova type 2. A supernova type 2 is a high mass star, that has enough energy to forces the core of the star into further and further nuclear reactions, and the formation of atoms not past the carbon and oxygen level. And that's what you're seeing in the simulation. And then it gets to the point that eventually the core becomes an iron core that cannot be fused into heavier atoms and release energy. This core contracts quickly, in fact, very fast, and the outer layers expands. I really don't know what's going on here. And the outer layer expands into a supernova type 2. Okay. The importance of supernova type 1 is we know the amount of mass that has been converted into energy, 1.4 solar mass, and because you know the total power, the total luminosity of that content, you can, by using inverse square law, you can establish with somewhat precision the distance to that explosive center. White dwarfs. So white dwarfs are the end of line, are the main result, or the main end of life of a low mass star. And by definition, low mass stars are those with less than 8 solar masses. So more than 8 solar masses, we consider them high mass star. Now, what is important about this low mass star? Chandrasekhar, there you go, here, Chandrasekhar. He was an Indian astronomer working in British, and he calculated this limit. So if you packed electrons as much as you can in a high density condition and situation, you cannot go above 1.4 solar mass with this packing process without forcing electrons into the protons, into the nucleons, and initiating a further process, which is the explosion you just saw. So white dwarfs, they cannot be more massive than 1.4 solar mass. And it so happened, if the white dwarf happened to be a member with a binary, in a binary system with a companion, so this white dwarf will start eventually dragging material onto the central star, and because of a gravity pull, and this material following in the white dwarf will slowly increase its mass to the point that perhaps it's going to reach this limit. And when it does, kaboom, you have the supernova type 1. There is another phenomenon associated with this, and that is not the supernova, but the nova phenomenon. So exactly what is this? So you still have a compact degenerated star, which is a white dwarf, in which the gravity at that location is phenomenal. And then if the companion that is part of the binary system is transferring material, this material falls on the white dwarf and packed at very high density. And eventually this high density cover or coating surrounding the white dwarf, made of material, freshly material that came from the companion star, gets a flash. It initiates fusion reaction in a short amount of time, and that releases energy, and we call that nova. Nova is a Latin word. In fact, it means new, and that's how people surveying the sky in olden days thought stars would be formed. Suddenly they flash and they come into existence with the exuberant production of lights and energy, which is completely, totally different from what the reality is. So stars, they initiate their life cycle pretty much mild, and they are low. They are of low temperature, and they are pretty much dim. They are not luminous at all. There he is. There he is. Um, Here is the evolutionary track of a star like the sun. This is the main sequence in an HR diagram that relates or locates and its locale of the stars. They are undergoing fusion reactions. So the star, like the sun, it goes through this phase of becoming a red giant, horizontal giant branch star, and eventually a symptotic giant branch star. And eventually, these energetics in the core is exhausted. And when that happens, oh, you are being filmed. And when this energetic occurs for the second time, when helium now is, or the core of carbon core is being slowly contract, the outer shell expands in asymptotic giant branch star (AGB). Then the star really rises in its luminosity, becomes as big as it can be. In the case of the sun, think about Mercury being pretty much engulfed by this expanding outer shell. That it will find its way through the interstellar medium, which freshly produced carbon and oxygen, and so, and then eventually all this shell is gone, and what is left of that system is the degenerated core we call white dwarf. And the white dwarf is small. It's the size of our planet Earth. It's not big at all. And so think about the sun is about 100 times as big as Earth. The core is the size of Earth, so it's 1/100th of what the sun is right now, and that is the size of a white dwarf. And so because it's small, although hot, it's not luminous, and then it appears in the HR diagram in this particular location. Now, planetary nebula are the most fantastic or beautiful pictures there are available online. Let me see if I can pull some of them. And we saw in that video, look at this, they are really quite something. This looks like the one in that video we just saw. Have this. Oops. What is it? I didn't ask that. Huh. More of them. Yeah, I don't know what this is. This is suspicious. Doesn't look like a real picture. This looks like a real picture with the processed image, but not the other one. Okay, so planetary nebula. So a planetary nebula, you look at these pictures, you always see the expanding shell. See this bright thing in the center? This is the white dwarf, pretty much exciting the outer shell. Look at that. That might be the central white dwarf. Well, I don't see it here. Don't see here. I might be able to see the white dwarf. I mean, this blob is not the white dwarf. It's just pretty much some of the gas that is being excited by the white dwarf. There you go. Can tell there. How about that one? Oh, there's the little dude in there. See that? So planetary nebula. Oh, I think I lost my. Oh, right here. No, no, that's not it. Where's my book? Oh boy, I lost my book. Oh, that's me. I did lose my book. Sorry about that. Quickly, astronomy, and download a PDF, low resolution. Let's go to chapter 25. No, 23, I think. There you go. And there. So mass at least 8 solar mass or above, they are considering high mass star, and their evolutionary sequence will lead to this, an iron core that cannot be fused anymore into some heavier atom. And what we saw previously in low mass star were the carbon and oxygen core surrounded by a helium flash or helium shell with fusion reactions plus a hydrogen shell with fusion reaction. So in the case of a high mass star, you have those two plus carbon plus neon plus oxygen, silicon, all of them fusing together. So the amount, the quantity of energy coming out of this central part of the star is phenomenal. So all of this is driven again by mass. So more massive stars will be able to exert some higher pressure in that region, accelerating these fusion reactions basically. And as a result of it, the significant amount of energy coming from the center part enabled the star to expand to the size of what we call supergiants. So supergiants are high mass stars that are leaving the main sequence. Again, mass determined their lifetime in the main sequence, and these high mass stars stay very short amount of time, and then eventually they initiate their post-main sequence phase, in which case they navigate in the HR diagram in that upper part of the diagram. So let me show you simulation that really exemplify very nicely HR diagram and the different parts of it. And we have been exploring this in our astronomy lab class. So this is an HR diagram that relates energy and surface temperature. Energy and surface temperature sometimes appears with spectral type, which is the same thing. But if you allow for the nearest stars, so stars, if you take stars in our vicinity up to 15 light years, this is what you got. You're gonna get most of them are subsolar and they are cold stars, right? And if you look at this little dot up here, this is Sirius, the brightest star in the sky, 10,000, about 10,000 surface temperature and a luminosity of about 20 suns. That's Sirius. But if you allow for the brightest star in the sky, those you go outside in a camping site and you see Arcturus, you see Betelgeuse, Antares, and all these nice um, Aldebaran. So those stars, they are luminous. But see, they are not the one next to us, like, with this exception maybe Sirius. So the stars, they are the brightest star in the sky that you can see without problem at night. They are somewhere here. They are either living in the main sequence, as you can see in there, or in the main sequence. I can show the main sequence. What is the class? Those are the two, the luminosity class. Okay, here's the main sequence. So stars, there are main sequence are right here. Those are the red giants, and see the supergiants. You don't have, there are few supergiants out there because this phase is too short. So basically, stars, they live their lives pretty much more than we do our lives. 100 years we are done. So stars live much longer. Excuse me. So and that's why the majority of stars in our galaxy are main sequence, because that's where most of the times they spend most of the time fusing hydrogen into helium in their very core, keeping the star stable as a result. But eventually this phase ends, and then the star goes through the plasma sequence phase. But those phases are very short, right? Compared with the whole lifetime of a star. So 5 or 10% of the lifetime is pause and pre-main sequence, and that's it, right? So to find the first of all, high mass stars are not common. First of all, so if you find them, to locate them in the supergiant phase is another issue, because that phase is too short. And here you find the white dwarfs. Okay. So as we saw, a star like the Sun evolves off the main sequence. It becomes a giant and a red giant, right? And then it starts fusing helium into carbon and become a horizontal branch star. Horizontal branch star. So the size doesn't change much, but the surface temperature does. And then eventually, carbon, or the helium in the core, is exhausted, and that star initiates its helium core, the carbon oxygen core contraction, and expands to become a asymptotic giant branch star. And then eventually it crosses over, because now it's losing material, and now eventually it appears right here as a white dwarf. And then you can see a white dwarf right there in comparison with our sun. It's about 1/100th of that size. It's an Earth-sized object. And a high mass star, if you think a high mass star, is right there in the main sequence, right? And then when it leaves the main sequence, it expands as a supergiant. See that? And those you can see it quite well, right? So they are huge. And then you can see how their radius change as a result of their expansion into these more exotic and dramatic phases. In all of that, what's the main result? What come out of it? What come out of it? What they spend so much time doing? I'll show you. It's right here. Atoms. So eventually, when they die, either exploding like a supernova, or exploding like a supernova type 1 as a low mass or supernova type 2 as a high mass, um, they 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 are responsible for atom production, and that's what you are seeing in this periodic table. So astrophysical sources of hydrogen, Big Bang, and it is essential to all life because you need water to survive, and water is made of two atoms of hydrogen and one atom of oxygen. So where is the oxygen? It's right here. So the red code here indicates that it's essential to life, right? It's the right hand side, the left hand side is astrophysical source. So the astrophysical source of oxygen is what? It's a kind of a dark blue, high mass star. And that's what we saw in those shells. So oxygen was one of the shells being burned, and that thing is, when it explodes, you have this freshly produced oxygen released in space. Let's take a look at lithium. Origin of lithium 2, cosmic rays. Essential to life, biological use, transported, reduced, methylated. I have no idea what that is. Beryllium, same thing, cosmic rays. Right. Lithium, beryllium, boron. Let's look at carbon. Carbon is essential to life as well as nitrogen. So nitrogen is what the plants need to survive, and that's what we need to survive too, because we need plants. Even those that are not vegetarian needs plants because they eat meat, and animals eat plants. But anyway, so it's essential to life. Carbon, nitrogen, and oxygen, and also they appear in the DNA sequence, right? In the DNA molecule. But what's the origin of nitrogen? So the origin of nitrogen is high mass star. And carbon, low mass star and high mass star. So we have two origins in there. So fellows, iron, so important for our blood. So if you are anemic, the doctor will prescribe you some iron, some pills, or some reinforcement. So where is iron? Ferro, 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 ferro. There you go. How about astrophysical origin? Supernovae, right there, supernovae, but also in high mass stars. So you have iron being formed in supernova explosion and in high mass stars. So which is the same. So iron can either be produced, excuse me, in the in type 2 supernova when that thing explodes, but also in high mass star. Okay. So today I was solo. I would like to remind you that we have an exam coming up, and as always, make sure you go to the end of your book and review the questions that are available in there, and I will craft questions taken from there. So the better you understand them, the better for you in the exam. And if you don't understand, or you don't know how to answer some of those questions, just talk to me or email me, and I will be glad to go through with them with you. Okay. All right. So have a good night.